Okay, look at solid. The solid form, ice is hard and rigid. A piece of ice has a shape of its own. Now you can see that compared to solid and liquid, has a shape of its own, it's rigid. Solid form, ice is hard and rigid. A piece of ice has a shape of its own. The strong bond between particles hold the particles together against the force of gravity and give it a fish shape. Right? Gravity is pulling it down. So because of the strong bond between the particles in the solid stay rigid, has a solid shape. It doesn't like liquid. Liquid we can see the bond are not so strong. That's why gravity pull it flow. Liquid form, water flows, has no shape of its own. It takes up the shape of container. Except conditions of zero gravity lah. That one you don't have to worry lah. So we know that there is weak intermolecular forces between particles in the liquid. This cannot hold the particles together against the pull of gravity. Density of liquid water is just slightly higher than that of ice. Only for ice and water is a particular different because ice float on water. Density of ice is slightly less than that of liquid water at 0 degrees Celsius. Steam is what we think of as water in its gaseous form. This has very much larger volume. Volume of steam compared to water is about 1,600 times than the water it produces. A low density and no shape of its own. Yeah, it's gas, so low density, doesn't have a shape of its own. And another term we are interested in, internal energy. Internal energy of a system is the sum of the random must be there, distribution of kinetic and potential energy associated with molecule of the system. Right? Memorize for solid and liquid. And that is summarized internal energy, sum of kinetic energy, sum of potential energy. For ideal gas, the internal energy is the sum of kinetic energy of the particles. Ideal gas, no internal molecular force. They are free to move freely. So there's no potential energy. So kinetic energy is the energy is kinetic energy only. Thus, internal energy depends on the state of system, whether it's solid, liquid, or gas. A rise in temperature is due to an increase in internal energy. Right? Where there's a rise in temperature in the matter, whether it's solid, liquid, or gas, it's an increase in internal energy. Or as we are going to derive this formula, right? A rise in temperature, which is the absolute scale, is equal to half average kinetic energy of a molecule. Okay, thermal energy and internal energy. Remember, thermal energy flow from higher temperature to one at lower temperature. So when it enters a body or matter, right, it enters a thermal energy, it becomes internal energy. It shows us there's a rise in temperature of the body. When matter is heated, it expands and its temperature rises. This rise in temperature is shown by the increase in kinetic energy of matter. Okay, so rise in temperature shows a increase in kinetic energy of the matter. Molecules vibrate faster like you solid. Specific heat capacity. Increase in kinetic energy for solid and liquid show a rise in temperature. Right? So wherever there's a rise in temperature, there's an increase in kinetic energy of the molecules. The heat supply is the specific heat capacity. So this one memory work. The specific heat capacity of a substance is defined as the quantity of heat required to raise the temperature of unit mass of substance by 1 degree. Right? Quantity of heat raise the temperature of unit mass by 1 degree. Unit mass means 1 kilogram lah. So if you have a substance, right? Quantity of heat required to raise the temperature of a mass of m kilogram. That's the substance, mass m kilogram. Change in temperature, delta theta equals Kelvin is mc delta theta. Right? Delta theta is final minus initial. Initial temperature I, final temperature F. Right? Or sometimes we call it a change in temperature lah, delta theta. So unit is either joule per kilogram per Kelvin, joule per kilogram per degree Celsius. Right? This is required in your AS also, because this one you all study in your SPM. Stop me if I'm going too fast. Usually the initial temperature is the ambient temperature lah, or the surrounding temperature. Right? Unit of C, Q divided by M divided by theta. Q is in joule, M is in kilogram, theta is in Kelvin or degree Celsius. So specific capacity, don't memorize, just know roughly the value for water. Right? That's for air. That's for copper. What does it mean? You can see water has a very large specific capacity. What does it mean? Means that a rise in temperature of 1 Kelvin, a lot of heat is required. Right? Water is a good coolant. Melting and boiling. At both melting and boiling, the temperature is constant. The temperature doesn't rise when there's melting or boiling. The heat supply is called latent heat. Specific latent heat, given a simple L of a substance, is the quantity of heat required to change the state of a substance at constant temperature. Right? Memory work. Change of state, constant temperature, and quantity of heat. For m kilogram of substance, the heat supply Q equals to ml. Right? In melting, we change from solid to liquid. In melting, heat supply goes to break the bond. There is strong bond there between the particles in the solid. This increases the potential energy of the molecule. The solid changes to liquid. Right? So solid like ice, melting to ice water. Solid, there's strong bond there. So they have to break the bond. So you have to supply heat. So that goes to the potential energy of the solid. So when the liquid melt, it becomes water at 0 degrees Celsius. Okay, remember, internal energy is sum of kinetic energy plus sum of potential energy.
Is it important for melting?
Yes.
Okay.
Right. So in melting, we are supplying energy to the potential energy part lah. Whereas for specific capacity, we are supplying energy to the kinetic energy of the molecules lah. Same, boiling from liquid to gas. In boiling, heat supply does two things. Both these go to increase the potential energy of the particles. This is what your syllabus say lah, but it doesn't say about, you have to explain in terms of molecules and particles lah. That is the only way you can explain. In boiling, heat is supply goes to two things. It does work to separate, right? So liquid state, they're close together. Gas state, they are far apart. So you separate the work done to separate the particles so that the intermolecular force becomes negligible. Right? That's the first part of the work done. And work done to allow the particles in liquid phase to expand against the atmospheric pressure. Then for the liquid particle to escape, it has to do work against atmospheric pressure. So for water to steam, the change in volume is about 1,600 times, right? From a small volume, expand to a bigger volume. Okay, so in boiling or melting, the energy supply goes to the potential energy part. Latent heat of fusion and vaporization, this is just for your info only. Know roughly lah for water. Right? You can see that latent heat of fusion is 334 right, kilojoule per kilogram, whereas for latent heat of vaporization is higher. You can see that about 7 times higher. Right? So of course you want to know the reason why. Thus we can expect specific latent heat of vaporization to be larger than the specific latent heat of fusion. Huh? Remember, in melting, you just break the bonds only. Whereas in boiling, you have two things. Work done to separate the particles from liquid state to gas state, and then work done to allow the particles in liquid phase to expand against atmospheric pressure. Right? From a smaller volume in liquid phase, expand to a bigger volume in the gas phase against atmospheric pressure. So that's why two source of requirement of energy. That's the reason why it's higher. Boiling. Right? This is for your info lah. No need to go too detail there. Boiling is a process. A liquid becomes a vapor in the form of bubbles throughout the whole volume of liquid at boiling point. The heat supply is transferred throughout the liquid by conventional current. The liquid changes to gas throughout the whole volume of the liquid. When the liquid boils, bubbles of gas form within the body of the liquid, and this then rise to the surface. Bubble is less dense than water, right? Bubble of gas is less dense, so it will rise up. Then we just apply the formula of PV. As it rises, the pressure becomes smaller, so volume will expand. Right? This bubble expands as it rises to the surface. As the pressure decreases, as the bubble rises, right? Higher pressure here, lower pressure at the top there. The bubble bursts at the surface. Boiling point depends on the atmospheric pressure. I remember these are all extra info. If you don't want to study, don't bother lah, because it's nothing mentioned in the syllabus. Old syllabus got lah. An increase in external pressure will prevent boiling until a higher temperature is reached. Why? More molecules of air. Higher atmospheric pressure means more molecules of air are above the liquid. So less molecules are able to escape. To escape, the particles of the liquid must have enough energy to knock against a gas molecule. Okay, try this one. Try this question. See whether you can get the answer. heater supplying heat at a rate of 23.3 watt takes 12 minutes to melt 50 grams of ice to water at 0 degrees Celsius. Calculate the heat supply and the latent heat of fusion. This is your AS work. Q
One is
equals to PT,
yeah,
power times time, right?
167
Power,
760.
12 minutes and change to second, and 60, right? So that heat supply, heat to melt the ice is Q equals to ml. So Q, we have calculated. M, change it to kilogram. L, calculate L. Can. Anything not clear?
Okay.
Try this one.
Yeah,
A bit
can.
challenging. 515 grams of water at temperature of 55.5 degrees Celsius is poured into a 655 gram glass container of specific capacity 843 joule per kilogram per Kelvin. If the initial temperature of glass 20 degrees Celsius, find the final temperature. Find the final temperature. I always understand the question. 20 degrees temperature of glass initially, temperature of water 65.5. The water will lose heat to glass, glass will gain heat. So the final temperature is likely to be somewhere in between. No? In this question, the hot water loses heat and the glass container gains heat. The final temperature is thus between 20 to 65.5 degrees Celsius, somewhere there. That's why we are supposed to calculate. No change of phase involved. So it's all specific heat capacity. Let the final temperature be theta. Heat lost by water, right? Hot water, MC delta theta. Right? Change the gram to kilogram. And then there's a specific capacity of water. 65 go down to theta. Heat gained by glass. Change it to kilogram. That's the specific capacity. Theta minus 20. So heat loss equals to heat gain. Okay. We assume no heat is lost to the surrounding. Can or not? And
Yes.
not clear?
Okay.
I've forgotten to comment on your last assignment. Your assignment is being very well done, except that your tendency is you've forgotten to explain. You do in your head, then you write down your answer without showing working. Cannot. You must show your step.
Oh, meaning
That's why you lose. That's where you lose your mark. Okay,
uh the assignment you give.
say again.
Wait, it's the waves, right?
Ah, wave and
Oh yeah.
superposition. No, you didn't show step by step. You didn't show your reasoning. You just show your second step. the first step, important. Formula important to be written there. If your working is wrong, your formula is there, at least you'll get 1 mark. It's the right formula lah.
Oh,
Formula show your
means I
reasoning.
didn't like write the conclusion answer, is it?
Say again,
Means I didn't write the conclusion answer.
you should show all the steps. That's why you lose mark. Very heavy rain. Okay, any more comment? Any more question to ask?
No.
Okay, then we carry on. We have actually more or less completed, except that now I go review over some of the experiment, mainly for paper 5 lah. Right, this is your SPM work lah. Just to review your memory there. This is your emitter to measure your current, low voltage supply. There's your rheostat. There's your thermometer. There's your heater. Right? Voltmeter is to measure the potential difference across the heater. Then there's your metal block. Lagging is just your insulating material lah. Measure the mass of the metal and the slots of the thermometer and heater are both filled with glycerin to improve thermal contact. Note the initial temperature, right? The slot there, you put glycerin so that there's no air there lah. Improve the thermal contact. Turn on the power supply and start the stopwatch. Adjust the rheostat so that keep the current constantly by adjusting the rheostat. And then note the current, note the voltmeter reading. After a certain time T, switch off the power supply and then note the highest temperature reached. That's the final temperature. And heat supply equals to heat gain by metal. VIP equals to MC into theta F minus theta I. Okay, we got 10 more minutes. Right? Where H is the heat loss. The value obtained is likely to be an overestimate, as heat loss to the surrounding would have raised the temperature higher. Right? In this experiment, there's going to be heat loss. So you've forgotten to calculate heat loss, then the T that you calculate is going to be higher because the heat loss is going to increase this temperature. So C, the actual value of C is going to be smaller. That's why it's overestimate. If there's heat loss in the experiment, state and explain how the experimental value of specific capacity is compared to the actual value. Right? You are lazy like me to think about all these things. Then one is the no heat loss. This one is corrected for heat loss. And then this is the actual value. Right? This one is incorrect for any heat loss. So you calculate out, and you can see that it is an overestimate. Okay,
Mm.
okay. Heat loss will make this one smaller. That's why this one will be overestimate. Right? There's another way of reasoning. Then latent heat of fusion. Then latent heat of fusion is the thermal energy required to convert unit mass of solid to liquid without a change in temperature or at melting point. Right? The key is unit mass, solid to liquid, without a change in temperature, right? Or at constant temperature. Obtain the mass of a dry, clean, empty beaker. That's a beaker, clean and dry. Obtain the mass. Set up two sets, exactly the same. One control set to deduct the mass of ice melted by heat and from the environment. Right? We set one set with two sets lah. One with the both with the heater lah. One with the heater on, switch on. One with the heater off, because you want to correct for the ice that is melted by the environment lah, by the surrounding heat. Turn on the joule meter. Right? Joule meter is to measure the energy supply. As the dripping of water from the funnel is constant, place a beaker each below the funnel and note the time. Right? When the dripping of water is constant, place a empty and dry beaker below each of them. Track the water for a known time. Note the reading on the joule meter. Then measure the mass of water in both beakers. Deduct the mass of ice melted by heat from the environment. If the mass of water collected is m and the latent heat of fusion is L, Q is the heat supply. Right? Heat supply equals the heat to melt the ice, ml. Comment. The value of L obtained is likely to be an overestimate, as we need to correct for heat loss to the environment. That's your heat loss. The heat loss to the surrounding would have made the ice melt larger. Right? Heat loss to the surrounding, if it has not lost the surrounding, will melt more ice. So that's why it's an overestimate. Right? It's just to explain to you. L measure is likely going to be larger than the true value. Heat loss by heater to the surrounding, so less ice will melt. So Lm is measured value. L is the actual value. Heat loss by heater, so Lm is greater than the measured value is going to be greater than the actual value. Since some heat is lost to the surrounding, right? Or as I say, measure M is larger if no heat is lost to the surrounding. So make this one smaller. Okay, or you can see from these two formulas. This is the actual value, this is the measured value. Specific latent heat. Half fill the kettle with water. Let the water boil until it's steady. Right? That is your top end balance or electronic balance. Note the reading of the balance. And after the time t, right? Initially read it. When it's boiling constantly, read the top end balance. Then after time t, read the balance again. If the specific latent heat of vaporization is L and the mass of water evaporated is M, heat supply equals the heat gained by water and loss to the surrounding. That's the formula. If we have not corrected for heat loss to the surrounding, then the value obtained is likely to be always an overestimate. Since the temperature is the same, the heat loss is the same for the same duration of time. Right? You can do it again. One time, the first one, set the power, note the time, right? And then there's the equation. And change the power, keep the same time. Right? The heat loss is the same. The power is different. The mass melted will be also different. So in this case, we subtract. 2 subtract 1, equation 2 subtract equation 1, right? The heat loss is eliminated, so we get our equation. Any comments so far? Anything to ask?
No.
Okay. To investigate the flow of water, this is your paper 5 lah. There's a funnel there connected to a tube, to a rubber band, or hose lah, connected to a pipe there, or tube lah, can be a tube or a pipe. Make sure this is horizontal. Sometimes you put a thread there to guide the water into the beaker lah. Right? There's your funnel. There's a rubber tube, horizontal pipe. You use your spirit level to check that it's horizontal lah. And then the water must be overflow lah. So of course you must have a basin down here lah to collect the excess water. So the parameters, right? Length of this tube, diameter of this tube, right? This height of water level above the tube, volume divided by time. That means the volume of water collected divided by the time collected. Is called volume flow rate lah. Filter funnel must be overflow with water. This one, the water must flowing out so that we know the height is constant. Right? So this can be used to some example investigate how the flow rate is affected by water pressure by changing this height, or by changing the length, or by changing the diameter of the tube, right? One by one. Don't worry about this gadget lah. Just simple apparatus. This one gadget is a bit more expensive, but provide a constant pressure lah. Right? That's where the water come out. There's that one keep the water constant lah. Excess water will go out here lah. And then since this is made of copper, we cannot see it, so we have to have a connected glass tube here, no?